When Elon Musk released the Terafab blueprints, people noticed a circle in the middle of the complex. Someone asked what it was. Musk replied with 2 words, and those 2 words revealed something nobody expected to find inside a chip factory. In early August 2026, SpaceX and Tesla released concept images of the planned Terafab facility in Grimes County, Texas. The renders showed what most people expected: a massive industrial complex covering over 100 million square feet. But in the center of the complex was a large circular structure that didn't look like anything in a standard semiconductor facility. Viewers immediately asked the obvious question: is that a particle accelerator? Musk's reply: FEL FTW, free electron laser for the win. 2 words that confirm the circle is not decorative, not an architectural feature, not a cooling system. It is the outline of a particle accelerator, intended to generate the extreme ultraviolet light used to print the most advanced chips on Earth. Let that sit for a moment. Inside what was described as the largest building on Earth, a chip factory, Elon Musk is building a particle accelerator. Not to study physics, not for research, to manufacture semiconductors at a scale the existing industry cannot reach. This is the part almost no mainstream coverage has explained clearly. Terafab is not only trying to make more chips than the existing industry can supply, it is attempting to change the fundamental method used to create the light that prints those chips. And to understand why that matters, you need to understand how chips are actually made today. Every advanced chip manufactured today is printed using extreme ultraviolet light at a wavelength of 13.5 nanometers. That light is created by a machine made by one company, a Dutch firm called ASML, the only manufacturer of EUV lithography scanners on Earth. A single machine costs hundreds of millions of dollars. Delivery takes years. ASML produces a relatively small number annually, enough to supply a tightly constrained global market, not enough to satisfy a facility at Terafab's planned scale. Inside those machines, a high-powered laser fires at tiny droplets of molten tin at 50,000 droplets per second. The tin becomes a plasma hotter than the surface of the sun. That plasma emits the 13.5 nanometer light required to print the most advanced chips. It works. It is extraordinary engineering, and it has hard limits. Each scanner needs its own dedicated light source. The process creates debris that contaminates expensive mirrors. Power scaling is difficult, and global supply is constrained by one company's manufacturing capacity. At the volumes Terafab is targeting, those constraints become a structural ceiling. The free electron laser is Musk's answer. Here is the architectural shift that most coverage is missing entirely. A free electron laser works differently from the plasma light source inside an ASML machine. Electrons are accelerated to near the speed of light inside a particle accelerator. They are then sent through a series of alternating magnets called an undulator. As the electrons move through those magnetic fields, they emit intense coherent light. By tuning the electron energy and the magnet configuration, the system can produce exactly the 13.5 nanometer wavelength required for advanced chip making. No molten tin, no debris contaminating precision mirrors, higher power potential, better energy efficiency at scale. But the most important difference is architectural. Current EUV systems treat the light source as part of each individual scanner. Every machine has its own plasma source. To add more scanners, you add more plasma sources. The relationship is 1-to-1. The free electron laser concept treats the light source as a shared utility, more like how a building shares electrical power or cooling that can feed multiple scanners from one central accelerator. At extreme scale, that difference changes the economics of the entire facility. That is the circle in the center of the Terafab render, not a machine, a utility. The light grid that powers the chip factory. Here is where intellectual honesty requires stopping. Free electron laser EUV is not proven at commercial manufacturing scale. No chip factory on Earth is running production wafers with an FEL light source. Several research labs are working on prototypes, but none have demonstrated the reliability that semiconductor manufacturing requires. The technical challenges are real. Building a conventional fab at Terafab size is already extraordinarily difficult. Adding an unproven light source architecture raises the degree of difficulty significantly. The bet only makes sense if the existing approach is viewed as a hard ceiling, not a temporary constraint, which is exactly how Musk has described it. The risk is real, so is the reasoning behind accepting it. Here is the deeper layer most coverage is missing. Terafab is not simply a very large semiconductor factory. It is an attempt to control both the production capacity and one of the fundamental physical inputs, the light itself, that determines how many advanced chips can actually be made. Most fabs still depend on ASML for lithography tools and the plasma sources inside them. ASML is a single point of failure in the global chip supply chain that no amount of investment can quickly replicate. Consider what that dependency actually means at Terafab's planned scale. Every additional scanner requires another ASML machine. Every ASML machine requires years of lead time. If the FEL approach works, that constraint disappears. That is not just vertical integration, it is the removal of a geopolitical and logistical dependency from the most critical step in the manufacturing process. Most people will continue to discuss Terafab in terms of square footage and investment dollars. The more important detail is the circle in the middle of the render, and the two words Musk used to confirm what it is. That circle is an attempt to own the light that prints the chips. This is gated. Subscribe. The next door opens soon.